Professor Anja Schlömerkemper from the University of Würzburg, and she will talk about variational model for the evolution of magnetostatic materials. Thank you.
Thank you very much for the kind introduction and also for the invitation to this workshop. I'm very pleased to be back here and to have all these memories from this 6-month program that I was also allowed to attend earlier. So this was a great time that we spent here, and it's great to be back to discuss the recent developments. So I would like to talk about a joint work with Barbora Benešová from Charles University Prague, with Šárka Nečasová from the Czech Academy of Sciences in Prague, and from a former joint PhD student of us, Jan Scherz, who graduated in Prague and in Würzburg. And like when I was here like 6 years ago, I also talked about magnetoelasticity, magneto-viscoelasticity. We had an evolutionary model, and I will come back to that later. I will do a quick comparison about this new approach and the other one that we had earlier. So the idea is to really combine magnetic properties, elastic properties, and evolution, and all of this in a variational model. I will first give you an introduction, give you an idea of the model, present the weak formulation, then the main result, ideas of the proof, and conclude. So what are magnetoelastic materials? These are deformable ferromagnetic materials. And the mechanical and magnetic properties of these materials are interlinked, they are coupled. So if you think of the magnetostrictive effect, which you, for instance, observe in ferromagnetic shaped memory alloys, then you have like a metal material, which is like this ferromagnetic shaped memory alloy, and you apply a magnetic force, and this would deform the material, okay, depending on the external magnetic field that you apply. So you have like the magnetic force field applied to this material, and this will make the material deform. And you have like applications and actuators which generate mechanical energy from changes in magnetic fields. And we have even like there's division of that. You can even have like also transport of drugs in your veins, for instance, by exerting magnetic fields. Sorry. And then there's the inverse magnetostrictive effects. This means that the magnetic properties of a material may change if you deform the material. And also there's applications in sensors and so on. And so for many decades, these kind of materials have been discussed. There have been lots of continuum models for electromagnetoelastic behavior. And I would like to give you a few papers, names in particular, for what has been worked on. But before I get there, let me just say what I would like to focus on today. It's like, again, a continuum model. We look at the quasi-static setting, so this means our evolutionary setting is by neglecting inertial effects. It's quasi-static. We look at non-conducting materials, as many of you are familiar with from micromagnetic theory. So we have a ferromagnetic material, and we are interested in elastic behavior with potentially large deformations. And from the variational point of view, this means that we work with the theory of hyperelasticity and the theory of micromagnetics, and we want to combine the two. Let me set up the frame. Let's first think about elasticity. We would have our reference configuration here. Capital X is the Lagrangian coordinate. We have a deformation eta mapping to the domain eta of omega 0 and mapping towards eta of x. So omega 0 is just a 3-dimensional bounded domain, so we work all the time in 3 dimensions. Eta is our deformation that may depend on time. I'll come back to this later. And our magnetization will be defined on the deformed configuration or the current configuration of the material. And this is like part of the problem. Those of you who have worked on this earlier may know or do know. Elasticity is phrased with respect to the reference configuration, whereas magnetism or Maxwell's equations are phrased in the current configuration. We will now somehow have to couple these. Then the energy function, sorry. energy function would like this. So here I integrate over the reference configuration. We have here an elastic energy that I want to allow to depend on the gradient of eta, so the deformation gradient. We allow for second gradients of eta. Here we have a magnetostrictive term, also anisotropy terms, where we have the coupling of eta, the deformation, and the magnetization. Then from micromagnetic theory, we have also the exchange energy coming. We have the stray field energy, m times the h. H is the stray field energy that we obtain by solving the stationary Maxwell's equation. And we have here a potential depending on m, which we will use as a purely magnetic part, and we will use this for modeling it like the saturation condition using a Ginzburg-Landau. So here's now the references I wanted to give. In general, there has been like work by Brown, Thiersten, De Simone, Dorfman, so that goes back many decades. Even like existence of minimizers to the stored energy functional have been considered in the static case by many people in the last decades. Also, the quasi-static setting was discussed in the compressible setting. But then there was always some other assumptions, let it be on the energy, on the, like here, for instance, the static case. Then in the compressible setting, so it's not the evolutionary case, there's a quasi-static setting here, though, with some other restriction. And then also by Henao and Strofolini, we have some work even extending it to the Orlic-Sobolev spaces. There's also work including inertial effects, but then they work with small strain. I don't read out all the names, but you can see them all here. And then there's models phrased entirely in the Eulerian coordinates. And this is the paper I was talking about like six years ago, where we had a model working purely in Eulerian coordinates, and I'll come back to that later. And also I would like to mention there has been work on thermodynamics. So it's a broad aspects, and let me come to what we do here. So this is again the energy functional, the slide that you saw before. And I would now like to come to the time-dependent setting, because that's what we are interested in. So now we start again from our reference configuration. What I allow for time t, so like the deformation to depend also on the time. So our current configuration, the deformed configuration, will depend on time t2. So then we have the deformation defined on the reference configuration. And here you notice I have the magnetization defined on the reference configuration, but it now has a tilde. The magnetization M I used before is defined in the current configuration, and this is just the magnetization pulled back to the reference configuration. I will need that later. Okay. Omega of t is then just like the deformed configuration at time t. We have the Lagrangian coordinates and the Eulerian coordinates. So now we would like to look at the equations of motion, and then I will also look at an equation for the magnetization vector. So for the balance of momentum, I will neglect the inertial forces. And so we have a 0 here, and then we have that it's equal to a divergence of sigma. Sigma is the first polar Kirchhoff stress tensor, which I'm going to define on the next slide. Then we have an external force, could for instance be gravity. And we have here an external force coming from the external magnetic field that is applied. So this H exterior means the exterior magnetic field applied to our material. And this is just like a pullback to from the deformed configuration to the reference configuration, and then the standard Zeeman term that we have here. This is an equation in the reference configuration. We are working in elasticity theory, so this is like what we would like to do. We have some boundary condition for the deformation eta on part of the boundary we only needed, and that's a given injective function. So now the interesting part is now what is the sigma? Okay, this is what we need to define, and as I said, we want to follow the variational approach, so we start from our energy and the dissipation. first Euler Kirchhoff stress tensor is then given by a variation of an energy that I still need to define with respect to the deformation, and this R tilde is a dissipation potential, the variation of a dissipation potential with respect to the time derivative of Et. What is the energy potential? The energy potential is the sum of the elastic contributions and the magnetic contributions. And just for mathematical reasons, we say whenever we have the determinant of the deformation gradient being bigger than 0, almost everywhere, then we have this contribution. Otherwise, it's infinity, meaning we cannot have like infinite compression. The elastic energy is assumed to be the standard hyperelastic energy depending on the gradient of the deformation. And then we add a term which ensures that our elastic energy density tends to infinity if the determinant of the deformation gradient tends to 0. That's this first term. And then we allow for a second term here, just depending on the second gradient of eta. This will give us some more regularity. The magnetic part of the energy is just coming from micromagnetics, and I already mentioned some terms of this. But now everything, it looks a bit more complicated. This is just because I pulled everything back to the reference configuration. Okay, but that's in the end, it's the same thing as before. We have the anisotropy part of the energy. We have the stray field part of the energy. This is just like the exchange energy, gradient of the magnetization, just pulled back to the reference configuration. And then here, this last part is the energy just depending on M, and this is a Ginzburg-Landau approximation of the constraint that the modulus of the magnetization is equal to 1. Okay? This is just saying modulus of M equals to close to 1. Okay, and now we have a dissipation potential, and this is part of the modeling, and this is sort of, I would say, part of the math that we were doing. In particular, this second part here is something that we sort of developed, if you like, throughout our analysis and through proving. This term turns out to be a good one, and I will talk about this later, and you will see, and I hope to convince you that this is a good one. The first term here is just the standard one that you would assume for Newtonian fluids. If you write this in reference configurations, it's just the gradient of just the norm of the time derivative of the velocity. So let me say the dt eta is the velocity, and we have the gradient of the velocity. Okay, that's the standard term, and this term here is in the end just the time derivative of the magnetization squared. But we'll come back to that. It's related to the transport. So we need a few more things in particular. So this was about the equation of motion. We also need an equation for the magnetic force balance. And that's as follows. We have like a gradient flow. We have, let me go to the next slide here. We have a transport for M, denoted by dTm. We have this one, and this is like now put to an equation like the following. We have the external contributions here, and then these other parts are all coming from the energy. It's just a variation of the magnetic energy with respect to the magnetization. And this is now phrased in the in the current configuration. Let me write this in a different way. I think this is easier to grasp. So this is just a gradient flow for the magnetization. So we have the time derivative of M, capital dTm, is minus the effective potential. And so we can just write this as the variation, minus the variation of the magnetic energy and the external contributions. Or even written in a different term, again equivalent, we can write it using also the dissipation potential. So what do we have here? Again, this is like the term from here, dEm. Then we have this term coming from here. And this is now the potential, the dissipation potential. If I look at the variation of this dissipation potential, we come back to this also later, with respect to the third component, and we will just get this expression. And this is somehow the clue and the interesting part, that we just found the right definition, let's say, of the dissipation potential to make this sort of consistent and to make this. Okay. We need some mathematical assumptions on the different parts of our energy, and this is, I would say, standard assumptions. We need some regularity assumptions on the elastic part of the energy, on the anisotropy part of the energy, and then we have some growth and coercivity conditions on these potentials. And the details are not important for this. The stray field, I would just want to mention it here, is like a solution of the Maxwell's equations, and we have just like this, like Poisson's equation that can be solved here. Also, the details are not important for this talk. I would like to point out that we have a relation between the magnetization in the reference configuration and the magnetization in the deformed configuration. And there's some transport behind this. And this is like physics which is behind this one. And this is a transport we've been copying, let's say, from other papers. Earlier work, we find it in several papers. But that's the most simple transport you can assume, which is just saying like the magnetization is just sort of transported like a scalar and not like a vector. Okay? But that's somehow something which has been used also earlier. It's crucial for our work here, for the math. Okay, let's summarize the system that we have so far. It's like the equation for the for eta, the balance of momentum, boundary condition for eta, and then we have the equation for the magnetic force. In big formulation, again, I have just one slide with all these assumptions, which maybe I don't want you to read even. It's just like the technical assumptions that we need on the domain, that we need on the boundary. We need to have some certain parameters, need to satisfy some conditions. We need to have some regularity assumptions on the external forces, or like data. We have some assumptions on the initial conditions and on the functions C and W, as I mentioned earlier. And all of this I will summarize as assumption A, and in the theorem I will just refer to this assumption A. Okay, and you know, somehow have an idea where it comes from. Now, dealing with these deformations, and as I said, we want to work in this framework with large deformations. We also need to think about like injectivity of the deformation, and we ensure that we deal with the injective functions eta by assuming this Jalinetzsch's condition. It's this one which we impose up here. So we define the set E as all those deformations eta being W2Q, so relatively high regularity, which is why we have the second order gradient of eta in our energy functional. We have this eta being in W2Q. We assume that the elastic energy is finite. We assume that the Jalinetzsch's condition is satisfied and also the boundary condition. So this is our set curly E. And with this Jalinetzsch's condition, we know that any deformation eta in that space is in fact a global homeomorphism. This is what we did. And by Morris embedding and Q bigger than 3, what we assume, we know that all our deformations are in fact C1 functions. Then by the work by Healy and Krömer, 2009, we also know that the determinant of the deformation gradient is strictly bigger than 0 in our reference domain. This is important, so we know that hence eta is a global homeomorphism. Yeah, which allows us to always do this pullbacks. Now I can give you the definition of the weak solution. So let all these technical assumptions in assumption A be satisfied. Then we state that then we define that the system of these equations, the balance of momentum, the magnetic force balance, and the boundary condition has a weak solution on this time interval for some time t bigger than 0 if there exists a function eta in L infinity 0 to t and e, the set of all our deformations, and m tilde also being in L infinity h1. With the following properties. Again, we need this regularity for the time derivatives, and also we know that the m satisfies this transport that I pointed out earlier. Moreover, let me make first a full stop. So we have all these three conditions. And maybe here, if you look at this function space here, there's something I would say special. So usually if we have these Bochner spaces like this, the second space here also just depends on, for instance, the reference configuration. It's not time dependent. Whereas here, I want to allow for time-dependent spaces. Our deformed configuration can vary in time. Okay. This is what we allow, and I will give you a definition of this kind of space later. But that's also what makes it a problem, because we want to allow the material to deform. It's not constrained to a container, a fixed one, but we can deform the boundary. Okay. And of course, now we have all these regularities, and of course, our functions eta and m tilde need to satisfy the equations, and this is the equations in weak form. So first of all, we have the equation of motion, and here now I use the notation with the variational approach, so where we have the variation of the energy with respect to eta. We test it with some chi in these function spaces. Then we have the contribution from the dissipation part, and we have the external forces. Moreover, we have the magnetic force balance. Again, here we can say work with the energy, the variation of the energy with respect to m, and the variation of the dissipation function with respect to the time derivative of m, and some external forces. And we have initial conditions, and this is then satisfied. So if all of this is satisfied, we say that we have a weak solution. So let me now say what these more generalized Bochner spaces are. What do we understand by this? So I would like to define this kind of space here, a space LP, depending on time, with values in WKR, so some Sobolev type function depending on a deformable domain. Before we get there, let me say again that we have these deformations, eta, in L infinity 0 to e. We know that the eta of t is in the interior of this set E even, and we have a finite elastic energy. Moreover, since eta is injective in omega 0, we know that we have an inverse function, eta to the -1 at this time t, mapping to omega 0. So for each time t, we can define this function. And this function we use down here. So look at the function m, some function m that I want to be in that space. We somehow go back from the domain omega of t to omega 0 through this function here. And you see here, this m is defined then on omega 0, and so I can sort of express everything with respect to the reference configuration. But I say that we have functions m here, depending on time, with values in this sort of bit strangely written space. This is like functions and Sobolev functions on omega of t, and we here somehow take the infinite or the uncountably union of all times. So now maybe looking at the corresponding norm. So under the assumptions that I mentioned earlier on the deformation, we can show that this is in fact a Banach space with the norm as expressed here. So if you just do this formally, it's very easy. You just replace the standard domain that you have here by a domain omega of t. Okay, and then you integrate. That's very similar, but this is mathematically a technical issue that needs to be done. However, we now have like the definition of the weak solution, and now I want to give you the existence result, and it's like probably about the weak solutions. Exactly. So let the technical assumption A be satisfied, then we say that there exists a time t prime bigger than 0 such that the system, balance of momentum, boundary condition for eta, and the magnetic force balance admits a weak solution, eta and m tilde, on that set, on that time interval from 0 to t prime in the sense of the above definition. And moreover, we can say that the time t prime can be chosen as like the first time at which there occurs some self-contact of the material, and or that the energy tends to infinity. Okay, now let's see, what is the restrictions of our model compared to the earlier ones? We have a gradient flow equation instead of the full Landau-Lifshitz-Gilbert equation. We neglect inertial effects, however we have the quasi-static case. And our energy, the elastic energy, depends on the second deformation of the deformation, and also we have like the inverse of the determinant of the deformation gradient. This is like restrictions. However, now I would like to compare to the model that I discussed like 6 years ago when I was presenting a seminar here. We can now solve for the deformation itself and not for a deformation tensor that we did earlier, and that we could only do by regularizing a transport equation artificially. Yeah, this was just an artificial regularization. We can now do it without. Also, the deformation can change the shape of the material. So this is included, and this is something which we really are proud of, that we can do so. Also, we can work with compressible materials. And from the elastic point of view, we do not assume that the energy is convex. We can deal with non-convex elastic energies, and this is something nice to have. So what are the ideas of the proof of this theorem? The proof follows the implementation of the Georgi's minimizing movement scheme. In particular, we follow a work by Beneschow, Wackham, Schulte, and Schwarzerer that they published on hyperbolic equations and like fluid structure interaction. And the idea is to split up the time interval that we work with into discrete times, delta t, and so we have k times delta t as our discrete times. And at each discrete time, k delta t, we solve a minimization problem. I still need to tell you which minimization problem, that's part of the proof. But we solve a minimization problem and then obtain the Euler-Lagrange equations, and by this then we have approximations of the equation of motion. And then we pass to the limit as this delta t, the time intervals tend to 0, and we obtain the solution of the original system. I think I will have it on the next 2 slides, but I would like to stress it here. It doesn't matter if I repeat it. By doing this minimization problem here, we do solve for the magnetization and the deformation at the same time. This is sort of the crucial part of this method. Yeah, we can do this at the same time. I'll come to this later. It's already here. So it allows us to handle the non-convexity of the energy, because like for other proofs, also the one that I was presenting 6 years earlier, we were using fixed point arguments, and for these fixed point arguments, we use the convexity of the energy. Okay, but these minimizing movement schemes avoid this use of the fixed point arguments, and we can solve it simultaneously for the ether and the magnetization. Another aspect that we sort of avoid by that approach is that usually, or in other approaches, when we come to the direct discretization of the equations, we need uniform bounds for the appropriate deformation. And so then we have some kind of estimates of this form, where we have the energy at step k, energy at step k minus 1, and then we want to estimate it by something here, depending on k and k minus 1. However, also for this one, we somehow need the convexity of the energy, which we try not to assume, and which we are able not to assume by this other approach. So how does this now work? And this I would like to mention a few steps. I will give you on the following slides the definition of a functional F tilde, which will be made up of the energy and the dissipation potential. And what we'll do is then, for each time step k, we look at the minimization, and then we assume that we know the minimizer at step k minus 1, two functions. And then at step k, we know that the functional needs to be bigger if we evaluate it at k minus 1 expressions than the one that we are now looking for at time step k. So the problem is we want to consider this minimization. Find a minimizer eta k at time step delta t, m tilde k at time step delta t in this space E for our deformations that I defined, and the m tilde is just a function in h1 of omega 0. And you see here, maybe you notice we here work really in the reference configuration. So eta and demagnetization both are considered in the reference configuration of a functional F tilde, which is on the next slides, and so we minimize this. The functional F tilde is given by the energy potential, I define in a second. Then we have delta t times the dissipation potential in the discrete setting. Okay, what do? Instead of having the time derivative of eta, we look at this expression here, eta minus at k minus 1, the deformation, the minimizer at time step k minus 1 divided by delta t, and similarly for m. Then we have here the expressions of the external forces, and also here. The energy potential is the elastic energy that I defined earlier, and the magnetic energy that I also defined earlier that comes from micromagnetics energy. And now the sort of new part is, if you like, the dissipation potential. Again, as I said earlier, this is the gradient of the velocity squared. And here we have somehow the gradient of the capital dt m tilde. And I would like to skip over this. This is like just the definitions. How do we deal with the external forces? How do we discretize them? It's somehow done in the same way, but let me jump over that. And the approach allows us to handle the coupling between the equation of motion and the magnetic force balance. And as I already said, we can minimize this at the same time we have the discrete approximations of the deformation and the magnetization together. They are coupled, and also like physically, it's very natural, yeah, that we would say the energy of a system, that's what nature does, isn't it? Like minimizing the energy by changing ether and the magnetization at the same time. And then the existence of the minimizers of the discrete variation problem is just using the direct method of the calculus of variations. Let me comment on the choice of the discrete dissipation potential. Let me jump directly. I've already mentioned this one. This is like the ansatz that we do for our, we replace the time derivative of ether by this one and the time derivative of m tilde by this expression in the discrete setting. And the difficulty, like when we were proving this and working on this, was we would like to, or need to choose the potential, the dissipation potential in such a way that we obtain both equations, the balance of momentum and the magnetic force balance, from the same dissipation potential. Okay? And then the key term was like this one. And the crucial one, part of this, and this is on the next slide, it's the same potential again, it's like the same expression here. This term does not depend on the time derivative of eta. So this means when, now think of the continuous setting, if I look at the variation of this expression with respect to the time derivative of eta, it's 0. And that's the good thing. This is just 0. It doesn't contribute if, for the equation of motion. But however, when we consider this one and look at the variation with respect to the time derivative of m, it's just the thing we would like to have. Let me mention this. So like when we look at the dissipation potential R tilde, this term, as I've just said, this term doesn't matter. And for the other one, where is it? Here. This is just giving us then the contribution that we are used to from the Newtonian fluids. That's just the standard. Okay, and then we have the magnetic force balance, and where we just have like taking the dissipation potential now in the current configuration just transformed. We look at the variation with respect to the time derivative, dTm, and then we obtain the result. Let me conclude. In this variational approach, we are able to have a quasi-static evolution of the magnetoelastic material. We can prove the existence of weak solutions, at least locally in time. And the main ideas of the proof was like to use the George's minimization movement scheme that allows us in particular to handle the non-convexity of the elastic energy. And the functional, this was the idea, and the discrete minimization problem can be modeled with the energy and the dissipation from the continuous system by doing that ansatz that I showed to you. And importantly, we can derive the equations of motion and the magnetic force balance by the same energy and dissipation functions. And so therefore we can solve for the deformation and the magnetization simultaneously. Open problems, how can we extend this to a system with inertia? We could think of a different transport for M, wherever this is really the chosen transport is crucial for the analysis that we did and for the choice of the dissipation potential. This is really interlinked. And we can ask, what about Landau-Lifshitz-Gilbert equation instead of the gradient flow for the magnetization? And I would like to recall that this is joint work with Barbora Benešová, Shaka Nechasova, and Jan Schertz, and this was published in the Journal of Mechanics and Physics of Solids, and it's dedicated to Kaushik Bhattacharya's work. So thank you very much for your attention.
Thank you very much for this wonderful lecture. Okay, questions, please.
So, this is a gradient flow, and you're using, at least when the external forces are zero, it's a gradient flow. So you use, if I understand correctly, Navier-Stokes damping, which has the advantage that it's automatically frame indifferent, but it's not usually what one would use for viscoelastic damping in a solid, right? And one of the problems is that at least for models, I mean, even in one dimension, you have a problem that for the viscoelastic, more viscoelasticity of rate-type damping terms, they don't give you a gradient flow, and that doesn't necessarily mean that you can't use minimizing movements.
But you were saying that we should maybe add another term to the dissipation function. Is this what you're somehow saying?
Yes, but I wonder whether I think you would lose the gradient flow if you did that.
Dissipation. So yeah, you were saying that maybe we should add another term here, and but then we would have another term in our equation.
The general frame indifferent form is the deformation for the purely Kirchhoff stress is the deformation gradient times a symmetric matrix function of C, the strain tensor, and its time derivative. That's the general sort of, and Navier-Stokes damping, I'm sure, fits into that. And I had another related question, if I could. When you said you had existence until self-contact or the energy blows up, so I mean that was something to do with the external forces, was it? Or I mean, if the external forces was zero, the energy couldn't blow up, or
if it's like related to this assumption that we have in somehow also in here, so we need to have the energy being finite in order to an ether to be in the space, and once this is
but
not.
I mean the energy equation would usually. I mean, if you had zero external forces, there should be some sort of energy equation that stops it blowing up, right? Or what is the issue?
I mean, we haven't investigated that further, I would say, but how does it evolve in time? Differently to what we did also with Francesco in another in this other model, but so you are somehow questioning whether this what I was saying here, that the T prime could be the time when the energy rises to infinity, that this maybe never shows up.
What?
Yeah.
I mean, you meant the total energy of the total sort of elastic plus magnetic energy.
No, therefore, I mean, this is just like, I would say it's just like for being cautious or whatever, like this is what could happen. Without that, as far as I remember, I think we haven't discussed this, investigated this further, let's say. And the one with the self-contact is also clear we would reach the boundary, but it's always about reaching the boundary of the set curly AE. Yeah, so this is like what can happen, that we reach the boundary of the set. So it's about this set E, and we would reach the boundary of the set E. And this is somehow when we reach the time T prime. So what can happen? So in particular that the injectivity is lost, or that the energy is infinite. So it's more like on this logical aspect, without having really investigated what the energy does. I think there was another question in the back, is it right?
So what would be the difference between this gradient flow and Landau-Lifshitz-Gilbert?
Difference between the gradient flow and the Landau-Lifshitz-Gilbert is that we would need to have a different energy and dissipation potentials. So like if we start from this energy and dissipation potential and we do the variation with respect to the state variables and their time derivatives, then we obtain exactly this gradient flow equation and the.
So suppose you didn't have just for the moment, the elastic coupling. Your gradient flow, would it's Euler, I mean not Euler-Lagrange, but would it reduce to Landau-Lifshitz-Gilbert?
No, we would need different contributions.
Entirely different? Or? Okay, that's the main
This is a math question, I would say yes, because if it's different, it's entirely different. But it's like, yes, you have these cross products in these.
Right.
So you somehow need to get those cross products, so I would say yes, it's different. I think I would start from the beginning again, really thinking about this. It's not just like we would use the same proof and would just do a little bit of an extension and then you have it. I would expect that we really need to do more.
Yeah, the cross products are typically because of the unit vector constraints. So, and you somehow have that built into. Okay.
Yeah, but you have this precision of the magnetization, which is not in this model.
I mean, when I think of London electric Gilbert, I think of that as being a linear combination of one energy preserving flow and an energy decreasing flow. So it seems you don't have the energy preserving part. This cross product is the one that preserves not just size of n, but also the total energy. So I think the energy expression would be the same, but you just have a different notion of flow, one that minimizes energy, the other one that preserves. Is that right?
So you think it would be rather easier maybe to extend it?
Not sure about that, but
Yeah.
but I think I think the energy expression would stay the same, but you'd have a different notion of flow.
No, I think we would have a different dissipation potential.
Yeah, there's a couple of thoughts I had. Let's see if, let's see. First of all, the energy that you set it up so that it has a mass, because I noticed that you put second gradients in the elastic energy, and they would control the exchange energy. So the whole thing would be, say, would have a minimizer. So then at that point, the George's steps would work, I think, because basically you do the gradient flow that leads to minimize. But, okay, that's not what I wanted to say, something else. So, okay, another related issue, we can talk later, but did you think about putting this in the context of Onsaga's principle? Because this would solve a lot of issues of how the dissipation term should be. And in a way, it's the Onsaga's principle, which is basically the way you're doing it, but in Onsaga's principle, well, it's a very good, I think, bookkeeping mechanism for this. And if there's a term that says not right, you will be able to detect it right away. But yeah, I'd like to talk to you some more. Now we're into negative times. Yes. So thank you very much. It was wonderful. Thank you.
Thank you.